We left off the last video in the middle of Hamilton's law. Sorry about that. I tried to wrap up an idea before the end of the video, but here we are. So we found that pressure and temperature are directly proportional. And the way that Hamilton did this, and later Gay-Lussac, was by experimentation. Putting a sealed container with a gas inside in a hot water bath, heating it up, and then recording that pressure also increased. So what this means that we can do is compare two conditions like we have previously. So at first, we've only heated the gas a little bit, and then in the second condition we've heated the gas up more. And what we find is because of this direct proportionality, because we can make a line out of this, it means that P1 over T1 is equal to some constant K. And I've colored it purple here just to show, oh, it's a different K from Boyle's law or Charles' law. So don't get confused. We just use K to mean, oh, some number, and it's the same. So if they're both equal to this constant, then they're equal to each other, and we get Hamilton's law, P1 over T1 equals P2 over T2 out of it. Avogadro is the only one who didn't do this empirically because he was determining, this goes hand in hand with his determination of the mole concept. So how he came up with the number 6.2 times 10 to the 23rd, 6.02, sorry. Avogadro developed a theory to account for the behavior of gases when they are measured under the same conditions of temperature and pressure. So Avogadro was looking at moles and volume. The nearest thing that we have to this in our daily lives is a balloon. So if the pressure and the temperature are constant, let's say you're outside at a birthday party and you're filling balloons with air, you blow more moles of air into the bigger balloon. If you stop halfway, you've blown less actual particles. And so Avogadro theorized this as a proportionality. So basically within a particular fixed volume, this particular cube is 28.2 centimeters by 28.2 by 28.2. That ends up being 22.4 liters at a pressure of 1 atmosphere and 0 Kelvin. It has a mass of 4 grams per mole. And it has 1 mole of gas. And so you can figure out what the mole number is by making the line. So you draw out here, and you say, okay, so here's volume, and here's moles, or actually probably vice versa, but, you know, we have some line. That means we have a fixed 0, and then we just figure out there's some way to count moles on the left. At the time they didn't have that, but we know now that this volume of gas at 1 atm actually ends up being 1 mole from the ideal gas law. And it does weigh 4 grams per mole. So helium does have a weight, even though we think of it as floating into the sky when we let go of our balloon. Just a point of chemistry history, Avogadro didn't actually determine Avogadro's number. He may have estimated it, but he's credited with the constant because he was the first to propose this idea where there is some number that describes the amount in terms of particles rather than just weights. And that particle counting, in particular for gases, is proportional to the volume that they take up. And it doesn't matter what kind of gas it is. So that's the revolutionary part, is that even though these samples of gas, helium, nitrogen, ammonia, methane, they all weigh a different amount in the same volume, but they're the same number of particles. And the reason that they weigh differently is because of their molar masses, not because there's more or less of a particle in the space. And that's one of the things about ideal gases, is that we don't care what the identity of the gas is. The rules are the same for everyone. There's a pretty good PhET simulation on gases if you're having trouble visualizing any of them, any of the laws. I'm also going to put up a supplemental videos page that'll have a bunch of links. UT Austin, I think. I don't know. So I'll have to go back and look at the videos, but there's a couple of videos put up by a university that are pretty good on gas laws if you need just another angle of explanation, or there's some practice problems they have too. So I'll be putting that up after all the videos for Thursday. We can visualize Avogadro's law two ways. The first way is just what we were saying before, is that volume and moles are proportional to some constant, and it doesn't matter whether we have helium or ammonia, they're going to have the same number of moles and same volume. We can also look at two samples of the same gas. And so if we remove half of the air out, let's say we have a filled helium balloon, we untie it and we let some air out, it's going to whoosh out because of the pressure, but then we seal it back up. You'll notice something about the balloon, right? The volume's going to decrease when you let out moles of gas. And so either of these two scenarios, both volume over moles is equal to that constant. And so we can set them equal to each other to get the law when we're comparing two different scenarios. The other thing about Avogadro's law is that it makes moles and volume proportional. And so when we talk about gases reacting, if it's at a constant pressure and a constant temperature, we can talk about them in terms of the coefficients of the chemical reaction. That means the number of molecules or moles, but it can also mean that the volumes of gas that are reacting are proportional to those coefficients as well. So we have an example problem here on doing that. Reacting hydrogen with nitrogen to create ammonia. So if you feel excited and you want to pause the video and try it yourself, feel free. Just write the chemical reaction and balance it, and then you'll be good. Okay, so solution is 2 volumes of ammonia that are produced. So in this reaction, if it were happening in like a balloon, basically, what we would see is the volume from the reactant side to the product side, it would start to decrease because we're combining 4 volumes, some unit, let's say 4 liters, and we're creating 2 liters per 4 that go in. So there are some interesting results when we have moles of gas on the left being different than the number of moles of gas on the right. In particular, next semester, when you guys talk about chemical equilibrium, that will become more important. So, and then we can just summarize all of the gas laws. Remember, all these K's are different, but, you know, it's some placeholder depending on the gas in the experiment. Sometimes not depending on the gas, right? Some of these hold true for whichever. Actually, I think they all hold true for any gas, ideally. And so what we want is to use these gas laws to solve problems. Again, temperature must always be in Kelvin. For the combined gas law, you can use any unit for pressure and volume as long as they match. And then look for 2 sets of conditions. So some kind of change has to happen to be using these laws. We have to have a condition and then a second condition. So an example of kind of those rules, a balloon has a volume of 1.42 liters indoors at 25 degrees Celsius. Let's say that your house isn't pressurized, which is, you know, usually the case. So you walk outside and it's freezing, literally, 0 degrees Celsius, but the atmospheric pressure is the same. It's a sealed balloon, so moles are the same. Assume constant air pressure inside and outside. So this is a perfect example for how to use gas laws, because we have an initial volume, or V1, and an initial temperature. And something is changing, so T is changing when we walk outside, and that's going to affect volume. So rather than memorizing all of these and picking out which one you need, it's usually best to just memorize the combined gas law. So if we take all of the different variables that describe gases, they equal some constant C. We'll see later that this is actually R. Sometimes the combined gas law isn't reported with moles in the bottom. I think that exclusion is not useful, to put it a better way. So you just want to read the problem to see which things are constant and which things are changing, and then you'll be good to go. So this is the thing to memorize. It's either P1V1 over T1 N1. I like to use initial and final, just because it's consistent with other ways that we describe things in science with initial and final. You won't see 1s and 2s very often the further up you go, although they're essentially the same thing, so, you know, whatever floats your boat. And yes, it is gas that floats your boat, because the hull goes under the water line and buoyancy. Anyway, okay. So we'll come back to this problem at the beginning of the next video. I have a written out solution for it. If you are like, I've been doing this since high school and I could totally just plug and chug, do that. Watch the next video. See if you got the right answer. Don't forget about sig figs. And to convert temperature to Kelvin. Alright, see you in the next one.